big thanks to the professionals that we have done to this presentation. We are really happy to make it and a very interesting very coming from this experience researching and also very fascinating with timber structure, population, and also fencing with then systems. And we want to do we have a presentation, a personal story, and also to share with all of you the amazing work that she was doing in these years, and also again some question discussion. Thanks, Sam. Thanks for your time.
Thank you. Happy that you're all clear. Also, thanks Nora and Andres for the invitation. If I understood it correctly, I'm the second BSS talk. And with that, also the second Belgian person. So, yeah, I normally give quite some talks, but they're always about structures and what we're doing, but never really about me. So I have to say I'm slightly nervous, and yeah, I hope at least there's some interesting thoughts in there for everybody. And, yeah.
We don't have to have numbers for this person, so we don't want to more present, but we need to yes, for these questions, curiosity, and also we have to enjoy us. Thanks.
All right, thanks. So, as I said, basically a bit how I got here today, what I'm doing at the moment, and which journey I took to get here. Before today, I didn't really actually think about this, so I did have to, yeah, dive through quite some, yeah, history, good moments, less good moments, good projects, less good projects. But yeah, I thought it would be nice to just present my own story. It isn't very shiny. It's also not always making a lot of sense how I ended where I am, but I think most of us can relate to that. So yeah, this is basically what I did in the last 17 years. The presentation did not move yet, but shall I give it a try?
Yeah.
Nope. Maybe I could. Yeah. Nope. Nope. We did test it before when it was try this again. I stopped sharing. Okay. Hold up. This one?
Now it's a nice
Tell me what I should do. So I start the presentation, then I should start sharing. we needed to work on this when they were also system go a bit faster. Something that was for you. Show the monitor. So okay. I'm going to have on my screen now. Change it. No. No. With my phone. Change the texture. It's okay. That should be fine. Extend. Yeah.
Sorry.
So, yeah.
Interesting.
Control A. Ah,
If not, we will have sorry for yeah, I should change.
All right. Good. Yeah, so I quickly made a bit of a roadmap for this in 2018. So I did a master in architecture engineering at the University of Brussels, the French one and the Flemish one in Belgium. Then I did a master architect in Stuttgart. Then I did doctoral research at the same university at the engineering department, and then I worked at Boeing and Roman, Chair of Engineering, so I was teaching, and since the last 4.5 years, I'm working at Design-to-Production. I'm a timber consultant and managing director. Let's start the story when I was young. So my passion for architecture, geometry, or timber, where does it come from? It's not as straightforward. I wasn't a kid who was like building Lego houses or putting timber blocks on top of each other. So I was not really driven by design and geometry, but as many kids, I had big dreams. I wanted not to become an astronaut, but a neurosurgeon. Why is it a question? I also have to think why. It's something that I always wanted to become. The reason why I don't really know, but I blame many medical TV dramas and television. So yeah, when I was young, I was really good at math and science, but biology was not really my strong suit. So when I was 18, I had to decide what I would study. Neurosurgeon was probably not the best option, as biology was not my greatest. So I decided to go for something very math, and that ended up being engineering. So not a very glamorous story, but that's how it happened. And my studies basically included structural engineering and architecture at the beginning, and I did my bachelor's at the University in Leuven, and then switched for my master's to Brussels, which I think was, for me personally, a great decision. When I was studying in my bachelor's, it was basically being deep in like all the general science engineering courses like mathematics and chemistry and mechanics and physics, and although I was not mathematics, it wasn't really thrilling to me. I wasn't very passionate about it. Like, it was okay, I engaged it, but yeah, it didn't set my soul on fire. And this was kind of architecture that was created, very strange, very boxy, very traditional. I also grew up in a very small town where the architecture that I knew was basically like a nice villa houses in the dunes at the beachside. For me, that was like the main architecture I knew. And then I switched to my master's, and quite the enlightenment awaited for me. So suddenly something really clicked, and I found myself being quite passionate. So my journey took me to like this thrilling world of unconventional design, lightweight structures, 3D shapes, parametric design, and it was the first time where I also really had the feeling that I had to be an engineer and an architect at the same time. I had to design and calculate geometry simultaneously, and form for those courses was suddenly a whole new world. That's also why I really started with membrane structures, tensile structures, then also what actually came connected tensile structures, also some sincerity and some compression-only structures. Maybe you recognize these two, the compression-only structure with also the previous BSS speaker, Philippe Block. But this was like more than a decade ago, so quite early version. And for me, it was super fascinating that these super lightweight structures were at the same time very strong and stiff, and material almost came to life, like the utilization factor of it. And at the same time, I was also the conductor of the ceremony, as the whole parametric design, I could generate different options, which, I mean, 10 years ago, more than 10 years ago, it wasn't so common to use parametric design, and it was really the first time there was a software, and you could play around with sliders, and instead of like the 2D catwalk, we could suddenly create 3D models which could change, and you could whatever do with them. And for me, like, two professors at the university were really the first ones to introduce me to this. That's the lab and my labs. They're also very driven with the lightweight structures community, and they really started to make me passionate about it, architecture and engineering. Took only 3-4 years. And then I decided I didn't study that. So I got a chance to do the architect master in Stuttgart, which is basically a step further than just architecture and engineering, but also bringing fabrication into this. So learned how to use a Cooper robot, some Python coding, and also had some more time to work with these super fascinating structures. And then these three things basically also came back into my professional life. Very early on, I did an internship with Roma in Vienna. I, of course, did some more traditional engineering at first, sales and calculations for tower in New York and so on. But I also got this project, the Dream Under the Sky. And it was quite nice because it was about time I really used parametric skills I learned in for real-time structure, and we linked it to parameter. So both had the design at the same time we had evaluation of some reflections of the structure and so on. So it was feeling really that I could, even though it wasn't an engineering office, I still had some control of design and what acting in it. Then a year later, I was working at Teufel Engineering Consultants in Stuttgart, and there I mainly worked with membrane engineer. And there's this amazing German software which is called Easy. Opposite to what the name intends, it is nothing but easy. So the software in the membrane industry is quite good tool for form finding, so analysis linked to some finite elements, but it certainly has got a sense of humor. It's quite a challenge to the interface is basically elaborate in the process without anything but straightforward. But yeah, I worked on attempts, not the most exciting ones, but they also need to be calculated. So yeah, there I learned quite a lot, and at the end I was quite comfortable with going through the process of form finding in membrane, creating such patterns, making all the special movements, the whole with blend and snow and everything that it all works out. And I started my research at the University of Stuttgart, and this was also a bit what I had done until now. I really wanted to go further into membrane structures, but not only membrane structures, having it combined with an active. And this was under Professor Knippers, and it was again quite a close collaboration between architecture and engineering and fabrication. And this was my very first project. It was in the entrance hall in the Museum of Science in Quito in Ecuador. We had a workshop with students for 3 weeks where we had to design and build this in the museum. We used a really cool tool, which with my former colleague Seiji Suzuki developed, and yeah, we basically sat there with the students and we designed a structure that has a bit, if we go into the architecture, like more public parts, more private parts, and a digitally fabricated bench in between. The whole structure was made of bamboo, so a very local, low-tech material. And the notable thing here was basically the syntax plane. So normally, if you have an elastic timber bridge out, the way the elements are put together is not that exciting. So we wanted to try out completely new syntax where things are running not very traditionally, and also with that, trying to create structural stiffness, torsion, and so on and so on and so on. So this led to this structure in the end. It went surprisingly well. We built this in a day and night, and it worked. As much as it can work in a 3-week workshop with 10 students, this actually felt quite stiff and stable, which I wasn't really hoping for. We still suspended it from the ceiling because as it's an interactive museum, there's a lot of kids and they will fall on it, and it was yeah, not so ideal. But it was a really good exercise for me, especially to also extend the design space of rituals and stuff. And yeah, there could be many opinions about this, but yeah. Then the second project was the ICD Research Pavilion from 2017 to 2018. I was the main and only engineer on the project. This part is just a small part of it, but I think it's pretty cool. Normally, if you have, I don't know if you all know what planning is about this, but it's basically if you have bow and arrow, you just bend something, you put strain there, and it stays in shape. That's it. So you have something tensile, which holds something just bent. It's all quite straightforward in 2D or in 1D, but things become linear attached, quite different. And then into tensile is also quite straightforward. If you have a stretchy fabric and some flexible rocks, and you find itself some geometry in the act, which you can form, find, and calculate. But for me, that wasn't enough. I wanted something structurally, so I wanted to use the membrane, which is the same material that they use for stadium roofs. So PTFE for glass fiber, so quite stiff. And the only way that it works is if it's properly tensioned. So, and pre-tensioning such a membrane takes a lot of forces. So I thought it would be a great idea that this active part would tension this membrane. We started, this was done with a whole bunch of students, so not only by myself. We started with fabricating glass fiber ring. Then this ring was tensioned in a jig where we could add membrane. So we over-tensioned it, and then the same on the other side, and release everything ideally the membrane would be tensioned and the whole structure finds its equilibrium. This worked really well. It was so highly tensioned that I could jump on top of it and it sounded like a drum. So it was as high tension as a drum, which was what we're going for. So yeah, this part was really good. And then this had to be placed into the actual pavilion, so the bigger hall of it, which is this structure. So it's also movable. So you have two on the other side of this side, basically two of these carbon fiber produced plates going into the base where a crane motor is attached to, and by leading movement here, the whole structure basically closes. All good and well, but again, this was fabricated by students. They're black carbon fiber plates in the summer. They easily turn up to 50 degrees. So the quality of the plates was anything but ideal. And if you work with such a high demanding structures, you do basically need covered material. So there wasn't too much room for failure, and it wasn't as reliable as an engineer would like it to be. So we also decided to not move it for public. I also kind of want to emphasize that a lot of work went into creating these pavilions on this one. So all the students and all the researchers put years of their lives into it. And this one, unfortunately, never has been published. But I do want to give some credit to everybody who was involved, because for me, it's still an extraordinary project. And even though it might not have been the most successful one, the research you learn and failure is maybe even more valuable than fancy pictures. So, yeah. And then my last project at the university was we had now this membrane statically into this bigger structure moving, but I wanted to have my membrane moving. And if you know something about membrane, it basically only has one state of equilibrium where it's not over tension so that it breaks, or when it doesn't start breaking. I mean, one way or flips symmetrically the other. But I wanted to have all the stages in between as well. So I wanted to have a structure that moves and that my membrane stays tensioned one way or another. So my first study was to kill it with my thin wood shell structures, or shingles, if you want to call it. And when you move to certain states, the shingles are touching each other in shell-like structure. The second idea was integrating like internal vats. So just didn't bring active elements, but for that you really need a very stretchy fabric, which maybe you already know I'm not the biggest fan of. And the last option was cladding or laminating a membrane with thin veneer. And when you bend it, the veneer basically, depending on the grain direction, starts slowly curving, which locally starts tensioning the membrane, which then globally we start to change the membrane. So that was cool. So I thought, let's go back. And for that, we created it's a pot which is standing at the half across the partners. And the idea was basically that's kind of a phone booth where you can sit and depending on pricing, you can make all good and well. Here, I underestimated a little bit the weight of the membrane, which, of course, through a traditional membrane is more a factor of 20 times instead of some extra kilograms. And we had to repeat so glass fiber rocks inside, and they were basically not structurally sound to keep the structure up. So it stood for a week at Foster Partners, and it was shipped to Copenhagen for exhibition. Here it also stood for a few weeks, and that was the end of its lifetime. So yeah, here you can see the back, which is actually so pattern was made with this system, and you can really see double curvature of the little shingles, which are state tension. So again, first of all, the success rate of the project itself, but yeah, I think it was quite interesting, and it also really expanded my knowledge and refined my skills, and yeah, a lot to discuss about this. But then I thought, good, it's time. Let's go to the real world and leave academia a bit and start to do some real tangible projects. And here again, we're coming into the crossroads of engineering, architecture, and fabrication. So for me, it's really interesting to bring these things together, because if the problem arises in one of the three fields, the other, or one of the other fields, always holds the potential of a solution which you might not have thought of if you solely stay in your own field. So even though this is a specialist talk, I don't really think I'm a specialist. I am more a generalist, which really which is a specialist in collaboration or synergy, or how you want to call it. So I really love to bring different things together, have maybe a different point of view of the solution, and really try to connect dots and see the big picture. And that basically led me to timber. For me, the intertwine between these three things is talking timber. So it doesn't require a form finding process like membranes or connected structures, but if you want to design with timber, you have to understand the material. So timber brings really together these three things. You need engineering knowledge. It's essential to really comprehend the structural properties and be capable of pushing timber or solutions in timber. Also, designing is very important. You really need to be able to see what you can realize and take care of the heterogeneity in timber and all the other. I mean, it's a lot of material, so you do, from a design perspective, you can bring a lot into it. And then, of course, the fabrication part, where how do you turn something to something tangible, which timber is perfect, because you can see that fabrication, there's a lot of possibilities. So then I came, so part of my research with the industry partners, it was not my industry partner, but from one of the team people with Design-to-Production. And I can basically pray for a few minutes freely why I took being a Design-to-Production. So it really was a company that, for me, embodied the vision that I wanted to go to in the future. So they were doing extraordinary projects with timber. For me, they really were masters of making things happen, of turning the impossible into the possible. So turning just ideas into a real-time structure, and by doing that in a quite like high systematic and like very clear process way. So yeah, for me, like I was quite confident, and I was also quite proud to start working there. Yeah, you probably know most of us, like these kind of projects I do. Accidentally, I pitched your one projects, but of course we do other things as well. So we have the Hasley British Golf Club in South Korea. We have in Bill Swatch headquarters, or France in South Korea. There was many other projects, but yeah, mostly ask people, what do we do? This is what comes up. And we're actually doing way more than that. So the digital planning, of course, is one part, but we also do consulting and software. This one will talk into sales talk, but maybe slightly a bit more understanding what I'm doing in the company. So we have software development, digital planning, and consulting. Consulting, where I'm part of, we have it on different levels. So project level, I think it's quite straightforward. We go to a project quite early on and try to improve the projects in every way possible. Structural system, how systematic details, how to assemble it, how the logistics work, which material, which products. So really pushing also innovation into these projects. Then we have our process level, which is not my department, where we really go to companies and like CAC equipment, digital fabrication process, demonstration, and so on. And then the last part, the company level, is I think what I do most. But I can come back to that in a second. Then we have the planning part where those 2-3 people work, where we're doing parametric planning, we created 3D models and application of that. That's also why the company basically started. And then the last part is also custom software development. So we do automate processes, have configurators for products, develop plugins, develop web apps, and so on and so on and so on. But back to what I'm doing. On project level, I will talk shortly about this one project. It's quite recent, and I'm also quite proud of it. And then on company level, I'll say what I'm doing there. And I talked already a lot about synergy and things coming together, but also here the disciplinary or interdisciplinary is quite nice because we have a lot of projects that are both software consulting or both consulting and planning and so on. So it's quite nice within the company. We have different units, but the projects where things come together for me, yeah, super interesting. I'm also not a good coder, so that's one of the only I think at the company. So for me, that was intriguing what software is doing or what the planning guys are doing. And, yeah. Project level. So this is the Wisdom in Stockholm. We finished it in September last year, and the structure was built or finished in December last year. And I really like this project because for me, it's like my whole career comes to a full circle with the project because we used Manufactured here and we used Timber, and it was real project and it's successful compared to most of my research. So yeah, I wanted to show some things about it. So it's an extension of the Technical Museum in Stockholm. It has a 3/4 roof, so pit shell. It's on 2 columns, and we have dome basically in the middle where we have the cinema inside. Maybe shortly some credits. So it's by Oscar and Architect, it's a local architect in Stockholm. We work together, so the team of timber experts with PAZ Central and SGB, so Swiss engineers, very good timber engineers, and then also Limam worked as fabricators. And material was sponsored by Stora Enso, which is very nice for the museum to have sponsored material, but that means we had to make the whole building in CLT and LVL. And as you normally know, we love to make rich shells out of aluminum, which in this case was not much. So LVL is a plate material, and we had to come up with a solution how we can turn this plate material into beams. We could do like glue and just glue everything together, but then it's basically more glue than wood in these beams, which we're not a big fan of. And at the same time, it would take so much time to, I mean, the plate tensile 21 millimeter. If we have to, the roof length is 47 by 20 something. So, I mean, it will take, I mean, it was a very short time frame. I was thinking about that. In a year and a half, went from like design concept to finished outside. So, yeah, here is where bending X technology came in, and where I could combine it with finally some good results after all my research, and where I could use it basically. So, what did we do? We have plates or put out plates, and then they come straight back outside. They find picks it up. Gravity already does a bit of help there, and then they get placed on this web towel and fixed. So then fixed. It's a very experimental project, which I mean, when normally research is fine, and if the results are not that good in the end, it's normally also okay. But in this case, there wasn't really an option, and we had a very extraordinary team. So we also worked together already for many years on projects, so we know each other, we know very exactly how to work there. So yeah, I think that was the first part of the success. And now, of course, we had to design an active project, which should not stand there for a few weeks, but preferably for the next 100 years. And we had to find a way that when we bend it, that it basically can keep its shape. So in this case, we don't want to use a membrane. We use wood towels. So we shear out the rubber towels, and they keep the bending and twisting of the shape. Of course, in research, it doesn't really matter if you're like 10 centimeters off. In reality, we're talking about less than millimeters. So everything has to fit perfectly. So we did decide to glue the first layer. So there's 5 layers of beams. So we glued the first layer, which basically like stay in place all slack. And then it was in the perfect position for the other layers to arrive, and where we had the exact geometry at the end. Among many other challenges, one was, of course, if you bend something, it wants to go out. So you have horizontal thrust forces, and normally with elastic grid channels, they're either going into the ground or you have columns which are aligned with it. This case is not that columns. So we have the giant group, the giant forces coming into our columns. So one thing the engineers came up with was pre-tensioning the column, which is also something that was done before. We also had this shear panel, which helped transfer loads from out of the solid shell into our column. We also had an edge beam going around, so quite a complex mix of geometry, because of course every angle was different at every column. Quite complex engineering as well, and it was absolutely amazing to come up with the whole team together, that the engineering is working, that in the end it looked exactly like the renders of the architect, that you could assemble it, that fabricated, which fabricated, and thirdly, at like a very economical way. And yeah, so lots of challenges where the team really came together. We're also having 2 papers of it, and one will be presented in 2 weeks in Melbourne at the IASS, where it's more about the collaboration between our parties, which was this project. But I think it's pretty cool. So this was a few weeks ago. They're still finishing the whole structure, but it's still standing, and everything looks great. Then the other thing is what I'm doing is rather on company level. So that's more about like big picture, so focus on like solving small details of the structure, really stepping back and looking at general construction as well. One example there is work with sort of like background department. It's an engineering office with some market analysis, which are normally done by like big consultancy experts, but this one I think is quite unique because it was really done from within the industry itself, with our knowledge, with our experience, and this was like one outcome where we mapped projects which were either solely timber or hybrid, and then the level like you engineered wood or just some timber, and then height compared to span, so height with level, buildings that span 50 bridges or large halls, and then on top of that, so things were mapped out in projects, also with bridge, if it was innovative, and out of that we could basically start having an outlook of where's potential, where they answer the market, also with their own background. They always did stadiums beforehand, like what is really the future in construction and what's their future in construction. We also mapped out different things like fabricators, what are the strengths, what is the can do, in which country, compared to what the high metal angle increment is. So that just means how much wood is growing in the forest every year, which we use, and basically see potential, because we don't like shipping timber all over the world. We prefer to build something to have local forests, local fabricators delivering to the project. So, of course, if you work in France, you try to build it in Germany, Switzerland, and so on. So, yeah, that's something that is very important to us. And the last thing I want to talk about is spreading the love of timber. So we kind of think it's our responsibility to also share more like our knowledge and our experience with timber. There's a lot of architecture offices and engineering offices that have never done timber before, really want to go into timber because no one wants timber is coming out. And we really try to organize workshops where we kind of give back knowledge, where they learn how to design with timber, learn what is important in timber, and also typical, the site engineer comes or the structure engineer comes and says, you can do this and this, that you do have this backpack and you can say, no, that we can do it like that. I know how timber works. And that's what we try to teach people. There's, of course, a lot of boring stuff we need to know. Some strength classes, the difference in brain direction, like how much difference there actually is. So we're not really, there we go. So the difference is about a factor and not just like adding a percentage. And we also show different comparisons between the construction system, whether there are advantages, disadvantages, what is the difference, sound logistics, detailing, material use, whatever you can come up with in small bricks and bigger bricks, larger spans, shorter spans, everything that you can think of. And of course, also some details. Sorry, got the detail animated. We'll take the lessons and we'll through them. Good. Yeah, so what kind of details are there on the market? What is important for yourself to design a detail? What is the advantages of one detail compared to another, and so on and so on and so on. And also fabricated, which is just as important. What tools are there? How can you make sure that shape of design is actually fabricated, preferably in a cheap or reasonable way? And then we also go we, colleague and I, designed this very architecture high quality building where a lot of problems occur, which we often say, and where we really go through the whole process of logistics, sampling, the structure system, different option, detailing, go to products, go to material, anything you can think of. And I think that one of the last things is teaching. So next to the work I did, I mean, not at the moment, but the last years, I also try to teach more, spreading the love of timber. I was teaching at the University of Stuttgart. It was called Form and Structures. I'm always impressed with, I mean, teaching is not for me, just sharing my knowledge. I think it's also great for the students, what they come up with in mostly naive minds still. They come up with crazy, great ideas. And I mean, some are like really cool, like the middle one behind the paper. They really developed a system for irregular table nets, which we with the paper that they had before they started course of being heard about table nets. So yeah, it's really nice. I was also teaching at Hardware, which I'm even more impressed about. It was an elective course for 3 credits. They never used Primer, they never used Grasshopper, they never heard about lightweight structure. And 3 credits is not a lot. So in Germany, you're 60 credits, so a few hours a month. But they were all super motivated. We basically used Primer Grasshopper as a tool to teach them structural design and how to form fine membrane, what is important in shell structures, in pneumatic structures, and everything like that. And in the end, they created pavilions, not just my drawing, they did also relations for it and everything that else with it. So just 3 credits. So I believe there's a lot of potential in the next generation. Yeah. So to finish up, we're at 44 minutes. Change timing. You also asked if I could share my future vision or how I see where things develop. So for me, it's quite simple. I think the use of more timber makes a lot of sense and it's supported, and it's quite important that it's used efficiently. So you don't want to use a bunch of wood just for CO2, which unfortunately happens a lot nowadays. You do want to use it in a responsible way, and the design should also be by understanding the material. I mean, I didn't really show an example, but Tamelia here from Shiradan is a perfect example of using wood in a way that basically describes it. And yeah, I think I'm going to leave it with that. It's my email address. You also can find it on our website. If you have any questions in the future, just write me. We'll always try our best to answer or find an answer or just tell you that we don't know. And yeah, if you have any questions now, I'm also happy. And if not, I'm also happy with it. Mhm.
It's about
Mhm.
the frequency.
So, I mean, materials are different, of course, in a different way that in timber you get the material and you don't create a material. In carbon fiber, you create a material which has many fibers you want in the direction you want, so it's a lot easier. Secondly, there was a lot more temperature and motion into the pavilion than there was in the group. And what I basically, the only thing I really used for this project was, it's going to sound very technical, but like secondary effects that torsion has in bending active. So you get like this membrane locking, yeah. It's deeper that space, which why using it, which when we work together with Kevin Blumer, if you don't know him, he's like the godfather of timber engineering. And we had quite a discussion early on where he said, out of my experience, it would be 40 millimeters thick, the blades would be able to bend and twist it. And then I was arguing, no, it's not possible because of this or that. In the end, I was right. I'm forever proud of that. But I think that's literally the only thing that really. I mean, research. So, I mean, in this case, you work together with 20 students. Here you work together with 4 specialists. And it's day and night different because they know what they're doing. They inform you of the things you don't know. Well, you're the one who should know everything. And yeah, that's it. So every step you do, you always have to test it. There were millions of 3D three-point bending tests, different material layouts, trying different resins, different fibers, just the material itself. There was no correlation between the material and setting up the material and final elements. So everything needs to be tested, that data needs to be transferred to it. And also the process, if you know anything about final elements, does not like large deformations. So we had to like hack the hell out of statistics to be able to just simulate it. And I think in the pavilion things were in the real structure things were a bit calmed down. Like, I think in the end the solution is much more intelligent and structure is much more, there's way more innovation in our building than there was in the research field, but there was way more variables because here we had a design, it's fixed by the architects, we have a cost, we have a timeline. This building was created faster than the pavilion. The pavilion took 2 years, this took a year and a half. So, yeah. Yes. So, there is a completely different dynamic, there's a completely different background and intent as well. Good.
Yeah.
Down with it.